Hello everyone, and welcome back to this second tutorial of pulse measurement capabilities. I'm Navneet Kataria and I'm the product manager for Andritsu vector network analyzers. In the last video, or the first tutorial of this series of pulse measurements, we introduced you to a lot of concepts related to pulse measurements, and that was an introductory video wherein we covered a lot of applications as to where and why pulse measurements are required and how VNAs are used basically to characterize various devices like radars, on-wafer measurements, and various other applications. We also saw that what are the important parameters and what are the important measurements that are required to be done, like pulse profiling, point in pulse, pulse to pulse measurements, and various other measurements as well. We also touched base on why pulse testing is required in various domains. Basically, it's a measurement which is more often used by radar applications or people who are in the radar segment, especially the system integrators, and as well it's used for on-wafer applications wherein the DUTs cannot be tested for a longer duration of CW waves, and that's why they need pulsing. The pulsing can be done on two grounds. One is the RF pulsing, and the second could be DC/IV pulsing as well. Andritsu has solutions for both, and in the last presentation we also discussed on the various solutions that Andritsu provided on the pulse measurement. We also touched based upon option 35 and 42, which are the two main options which makes Andritsu's solution the best in the world. Option 35, as you know, is basically the IF digitizer that we have in place, and that gives an unprecedented IF measurement bandwidth of 200 megahertz, which gives us a resolution of 2.5 nanoseconds in the pulse measurement. We also touched base upon option 42, which is basically the wizard by which a lot of measurements related to pulse which are not available anywhere in the world can be made very easily with this measurement. Coming back to this video, today we will be doing a demonstration of Andritsu pulse and various options that we have. Basically, I have a unit which is MS4644B. Today I'm using a 40 GHz vector network analyzer. Plus, I also have a pulse demonstration module which we normally let our guys who are there in the field use it for applications and demonstration purpose. So that module is basically used to give the RF pulsing capabilities. So this is how it looks. So you can see that this is a small box which has a power supply. Then there is an input which is coming from the pulse generator from the VNA backside. Our VNA has 4 internal pulse generators, and then we have the RF in and out going to respective ports of the VNA. Coming back to this pulse demonstration module, you can see this is the block diagram of this pulse demonstration module, and you can see it's basically a device which is trying to do a modulation or pulse modulation to the incoming RF from the VNA port. So you can see that the PGen low is closed. That means whenever we have to close the switch here to the RF side to make it pulse, so that means all the pulse modulation is happening in this box, we have to have the pulse generator signal coming in to be on the lower side. You can also see that there is a long transmission line which is shorted at the end, so there might be reflections coming out, and these reflections will actually coincide with the outcoming signal, and they could combine constructively or destructively. That's why the pulse may have some falling edges discrepancies, and that we will show you as well. Apart from that, we do have the pulse demonstration module component specification as well. We will be using a frequency of CW frequency of 10 gigahertz and the VNA frequencies to be operating from 5 to 15 gigahertz. And you can see that there are some insertion losses as far as this module is concerned. This can work up to actually 40 and 70 gigahertz. So you can see that there are some losses, and the specifications are very clearly stated here. There is some rise time as well, which is like less than 8 nanoseconds. But let's get going now onto the measurement capabilities.